Hi everyone, welcome back. In this lecture we're going to look at a technique known as Newton's method to approximating solutions to equations. So what's our big problem here? Well, our big motivating problem for this section is we want to try to find a solution to an equation of the form f of x equals 0. So we've got a function, we want to find its roots. Where does it cross the x-axis? Okay, so you may think, well, that's not such a big deal. I've been able to find solutions to equations before just using algebra, maybe quadratic formula if it was a quadratic. So yeah, we have techniques for finding exact values of roots of functions if the algebra allows us to do that. But the problem is we can quickly encounter cases such as, well, for example, what about this equation? Cos of x equals x. Can we find the exact value of the solution to this equation? Well, algebra doesn't seem to help us in this case because we need to sort of get a hold of the x which is trapped inside the cosine, but we also have an x outside. So, you know, algebra might not help us here. We might not be able to find the exact value of this, but maybe we're just interested in approximating the value. If we can't find it exactly, maybe we should be content with just approximating the solution. And that's what Newton's method is about. It's about a technique to allow us to approximate solutions to equations like this, cos of x equals x, or other equations where algebra is not going to help us out. So before we get into the nitty-gritty details, let's get a big picture point of view of what Newton's method actually is. And for this, we can use the applet that's available on the website. We have a function here in red. It's got 3 roots. And I've just chosen it so that we can easily see what the roots are, -1, 1, and 2. And I'd like to discuss the idea of how to approximate these roots. So what we do is we start with an initial guess. And I'll just drag x1 around until, you know, I think I'm going to try to approximate this root here. Pretend I don't know what it is. It's 2, but pretend I don't know what it is. I'm going to take that as my approximation. So 2.59279. Now, can I make that approximation better? Well, the idea is you head up to the curve and you draw a tangent line there. That's that green thing. Now that green line will intersect the x-axis at a point. It's got some x-intercept, so let's identify that. That's x2. Now what do we notice? We notice that x2 is a better approximation to the root than x1 is. And so that's the big idea. You start with an approximation, you do this tangent line thing, you get a better approximation. Now if we did it again, go up at x2, draw the tangent line on the curve whose x-coordinate is x2, and then find the next point, and we see that the next approximation of the root is even better than the previous one. So we seem to be getting closer and closer. I can do a third approximation. So we're getting really tiny to see on the graph itself, but we can see that we're honing in. We're getting closer and closer to that root. Now, all of this depended on my initial approximation. The rest was just mechanical. It was go up, find a tangent line, find the intercept. Go up, find the tangent line, find the intercept, and keep going. So if I had a worse initial guess, well, it would just take longer, but my next approximations would still be getting closer and closer to 2. What if I took my initial guess to be on the other side of the root? Well, it looks like we're still getting approximations that are heading towards 2. But what happens if I took my initial guess to be close to the other root, 1? Well, then my other points seem to be getting closer and closer to 1. And similarly for the other point over here. If I made a guess of about -0.42 or around -0.5, then the business of doing tangent lines to get intercepts, to get better and better approximations, seems to be going to that one. So it's very dependent on my initial guess, but the rest is just mechanical of finding tangent lines and intersection. So that's the big idea with Newton's method. Start with an initial guess and sort of crank out this procedure of finding tangent lines and intercepts to get better and better approximations. Now, things can go wrong. Here I'm interested in finding, maybe I'll turn off all of these lines and then we'll just focus on the points themselves. So here I'm interested in approximating this root. So if I get pretty close with my initial guess, about a half, I see that my next approximations seem to be doing a better job and they get closer and closer to 0. But suppose I made an initial guess of, I don't know, let's say 2.5. I didn't quite know where the root was, so I made a guess of 2.5. The first approximation, when I come up to the curve and take its tangent line, it fires me way off out here. So my next approximation is even worse. And then it just goes downhill from there. They keep getting worse, worse, and worse. So this can happen. It's highly dependent on your initial guess. If we made our initial guess on the other side of this bump, then they seem to be doing the right thing. They get closer and closer to 0. If I took the initial guess to be on the wrong side of the bump, then my next approximation seems to be doing worse and worse and worse. But that's the big picture of Newton's method. You want to find the approximation for a root, try to pick a nice close value, and do the tangent line business, find an intercept, and keep going and going and going, and hopefully you'll get a sequence of values that are getting closer and closer to the root that you're interested in, so you can find a nice, good approximation of that root. Okay, so now we've got the big picture point of view. Let's go through and try to see if we can implement this technique. So the idea is, we've got this function. Let me just get a rough sketch of one, maybe some function that looks like this. So this is our, let's say, y equals f of x. And it's got a root, and that's the thing we want to find. So there's its root. We'll call it r. We don't know what it is. That's what we're trying to approximate. So what we're going to do is, the idea is to let x1 be an initial guess. So we sort of try to guess what the solution approximately is. So maybe that's my first guess, x1. Okay, I'm not exactly at r, but can I improve this guess? Once I have an initial guess, can I improve it? And the idea was, well, you go up to the function, you look at the tangent line to the function at that point. So there's our tangent line at x1 comma f of x1. And what do you do with this tangent line? Well, now you look at where the tangent line intersects the x-axis. So what is its x-intercept? And we call that x2. So the idea was, you have this initial guess, which we'll also call the first approximation. It's our first attempt at approximating the value of the root. And then we get from that, through this tangent line process and looking at the x-intercept, we get a second approximation. And if everything's nice, then we expect that the second approximation to be better than the first approximation. So we have expected to improve our approximation. And so that's the idea. So how do we come up with an expression for x2? I mean, part of the implementation is we need to know how to find this x2 if we have the initial guess x1. So let's see how we can do this. Well, we're using the tangent line, so maybe that's the first thing we should do. So let L be the tangent line that we got at x1. What's the equation for the tangent line? So here, this is the tangent line at x1 f of x1. Well, we get that by taking the function value at x1 and adding to it the derivative at x1 times x minus x1. So there's our tangent line. What we would like is to figure out where this intersects the x-axis. So if we've called the x-intercept x2, then this means that plugging x2 into the tangent line should return a y value of 0. So this gives us an equation now for x2 in terms of x1. x1 is this initial guess, this thing we know. x2 is what we want to find. So what we're going to do is we're going to solve this equation for x2. So I'm going to push f of x1 to the other side of the equation as negative f of x1. Then I'm going to divide by f prime of x1. And then I'm going to push over the x1. And so I'll just move this negative down front. And what we have is an expression now for x2 in terms of our initial guess, x1. So the second approximation up here in the graph, x2, is just x1 minus f of x1 all over f prime of x1. So if we know our initial guess, we just have to work out x1 minus f of x1 over f prime of x1 to get the second approximation. Okay, well there's the game. The game is you've got the first approximation, you can use that to get a second approximation. Now if you just pretend that that second approximation, which should have been better than x1, we pretend that was our initial approximation and just iterate the process. Do it again. So we repeat this procedure to get a third approximation. How do we get the third approximation? We look at our approximation for getting x2 from x1 and we just apply that same thing now to x2. So we start with x2, we take away f of x2 all over f prime of x2. And that gives us a third approximation, which hopefully is better than the second. And then we can get a fourth approximation and a fifth approximation by keep doing this process over and over. To the approximation that comes out, we then feed it back into this machine where it says now take x3 minus f of x3 over f prime of x3. That gives you your fourth approximation. So if we keep repeating this process, then we should obtain a sequence of numbers, x1, x2, x3, and so on. And hopefully these are getting closer and closer and closer to the root, the thing we're trying to approximate. So if the numbers become closer and closer to r as n becomes large, then we say the sequence converges to r, converges to the root. And that's the key, is we can start with an initial guess and try to build up this sequence of approximations, which each one in the sequence is better than the previous one. So here's the process in a nutshell. We begin with an initial guess at the root. We then work out a second approximation using the first guess or the first approximation, and then we repeat the process. Once we have an nth approximation, we can get the next one, the xn plus first approximation, by just taking xn minus f of xn over f prime of xn and repeating. So this is called Newton's iterative formula. Newton's iterative formula means we're going to take this formula and we're going to iterate it. We're going to take whatever comes out and feed it back into it. xn comes out, you feed it back in, you get x plus xn plus 1. xn plus 1 comes out, you feed it back in, you get xn plus 2, and you keep going and going and going. When do you stop? Well, it's a good question. You continue this process until you have the desired degree of accuracy that you want. So suppose you want your approximation to k decimal places. Well, you keep going until you have successive approximations, xn and xn plus 1, agreeing to k decimal places. That's the good rule of thumb. You can stop once you get those two iterations agreeing to k decimal places, and now you have an approximation of the root to k decimal places. Let's have a look at how this works in practice. So we're asked to solve the equation 5x plus cos x equals 5. Now, remember, Newton's method is to find roots of functions. Here I'm asked to solve an equation. So the first thing we should do is push everything to one side. So 5x plus cos x minus 5 equals 0. And then we'll call this thing our function, because now we've just converted it to a question about finding a root of this function. So we're going to let f of x be 5x plus cos x minus 5, and we want to find a root of it. We want to find a root in the interval 0 to 1 to 6 decimal places. So Newton's method says, well, you're going to need to use the derivative. So that's 5 minus sine of x. And we're going to have to work out what the Newton iterative formula is. That is, the next approximation is obtained from the previous one by taking the previous one minus the function value over the derivative of the previous one. And in this case, f of xn is 5xn plus cos x sub n minus 5 all over 5 minus sine x sub n. So we're all ready to go. The only thing now we need is a place to start. An initial guess. What is our x1 that we're going to start to plug in? Well, we're given such a small interval, 0 to 1, that perhaps we could choose anything in this interval as an initial guess. Maybe it doesn't really matter. Maybe we can choose 1, maybe we can choose 0, and then just start to go and see what happens. And that's perfectly fine. You can try that. What I would like to do here is just indicate with this example how you may go about trying to get a good initial guess. A good initial guess for x1. The issue here is we want to find an initial guess to the root of 5x plus cos x minus 5. I'm going to rewrite that as cos x is equal to 5 minus 5x. So I'm interested in, so the root of f is really a solution to this equation, and I'm interested in approximating a solution to this equation. So the way I'm going to do this is I'm just going to sketch the graph of both sides of this equality. There's a cosine function. So the cosine function starts at 1 and comes down, and that's going to be pi by 2, and it's up here at 1. And then there's this 5 minus 5x. So 5 minus 5x, it has a root at 1. So pi by 2 is a little bit bigger than 1.5. So 1 is probably somewhere around here. And therefore our 5 minus 5x curve looks something like that. And this red one was our y equals cosine of x. And I want to find the x value for which they intersect. And that's going to be this value here. That's the thing I'm interested in. And I notice that, well, it's a little bit less than 1. Maybe I should choose 1 as my initial guess. Maybe I should choose a half as my initial guess. Both would probably be good choices. So what we're going to do here is we're just going to take x equals 1 to be our initial guess. Now we have an initial guess, we have our iterative formula, so now we just start cranking away. What is going to be x2? Well, x2 is x1 minus f of x1 all over f prime of x1. So that means plug 1 into the expression up here. So that's 1 minus 5 times 1 plus cos of 1 minus 5 all over 5 minus sine of 1. And now to work out cos and sine, we're going to need to use some computational tools, a calculator or a computer. In fact, I would encourage you to use a computer, and through this discussion, I'm going to show you the tools that you should be using rather than a calculator, because a calculator is going to get kind of tedious. You want something that you can go and quickly edit the code that you're entering and quickly do the executions. You don't want to spend all your time pressing buttons and trying to get these things in there, because this is an iterative process. We want to take what comes out and throw it back in again. And so I'll show you how to use a computer to do that. For right now, we work this out using a computer or a calculator, and we get the value of, this is approximately 0.8700736958. Now what do? Well, we take that number that just came out and we feed it back in to Newton's iterative formula. So now we take x2 minus f of x2 over f prime of x2. And firing that back in, doing the computation again, we get a value coming out of 0.87122141443. Now we take that number, we fire back in to Newton's formula, and we get x3 minus f of x3 all over f prime of x3, and what pops out is about 0.87122151545. How many decimal places of accuracy did we want for our answer? Well, we wanted to find the solution correct to 6 decimal places. So I look back now. Do I have 6 decimal places correct? Well, of course, I don't know the actual answer, so I can't compare this to the actual answer to know if I've got 6 decimal places correct. But we're going to use that result that I outlined on the last page. If the two successive iterations agree to 6 decimal places, then you know you've got the answer up to 6 decimal places. So let's just look. 871221. 871221. So they agree to 6 decimal places. So that means we found our answer. The solution to 5x plus cos of x equals 5 is approximately x is 0.871221, and this was correct to 6 decimal places. So we've got our solution that we were looking for. As you can see here, our calculations required quite a bit of technological use. We needed a calculator or a computer to start working out these values. But the goal here in applying Newton's method is not to do this tedious arithmetic. You want to have an understanding of the big picture and how Newton's method applies. So we have this iterative formula, and we have our initial guess. And having those 2 bits of information, the rest is just merely mechanical. You plug the value in, you get something out. You plug it back in, you get it back out. So you keep going in, out, in, out, in, out. And you keep getting these next approximations. This is merely computational. So if it's computational, you should be using a computer to do this. And I wouldn't use a calculator, use a computer. So how do you use a computer to do this? Well, I've got some stuff already written, so let's have a look at that now. So if you go to the course website in Canvas, click on Additional Resources. It'll take you to the Resources page, which contains a bunch of things I put together for this course. This page is accessible outside of Canvas, so I'll put the link in the YouTube description below for those who don't have access to the Canvas container. You'll see all the applets we've used over the course of the term, including the Newton's method one we just looked at. And this is the one I'm interested in here, Newton's method implementation. So click on that link, and it will open a page that looks like this. And there's a little scripting window in here. It's a Sage single cell. So what it's doing is it's taking whatever you type into here and sending it to a server that's running the mathematical software package Sage on it. It'll do the calculations on that server and then send the information back. So we've done an implementation of Newton's method in here. I've declared a variable, x. I've typed in a function, and this is the one we're going to look at, cos of x plus 5x minus 5. And then I've put in the Newton's iterative formula. Now, one of the things to notice is that I was able to use a diff command. What's the diff command? It's taking the derivative of f with respect to x. So here we're using a derivative command in Sage. So I'm asking Sage to compute the derivative of f with respect to x. And I'm going to call that new function df. And then I'm going to build this Newton's iterative function, which is, it's a function. It takes an input, what we've called xn in the past, works out f over the derivative of f at x, and then takes that away from x itself. Then I have to put an initial guess in. I've asked Sage to print out the initial guess, and then I've asked it to apply Newton's iterative method to that. So throw x1 into this Newton's iterative function and spit out x2. This capital N is just to turn it into a floating point or a decimal number, because it will return the exact value. And instead I want an approximate value in terms of decimals. And so I've done that a bunch of times using the previous one to spit into the function to return a new approximation, and we can click Evaluate. Now, one of the things we notice is that, yep, we've got x equals 1 as our initial guess, which is what we just did on the previous set of notes. So let's see what happens. Okay, it's going to ask me if I accept the terms of service, and there it goes. It's now spit out the values that we wrote down previously. So this is how I generated those values. I used a computer to do that. I could have done each step using a calculator or a calculator on my computer, for example, but instead I managed to put everything all in here and have it compute it for me. If I want more approximations, I'll just cut and paste the previous 2 lines, change that so that it takes the 3rd approximation in, returns that as the 4th approximation, and then I want it to print the 4th approximation. And there we go. If I wanted to change my initial guess, I can change it. Maybe I'll take my initial guess to be 2, and I'll evaluate. Maybe I wanted to change my initial guess to be 0, and evaluate. And in all cases, you'll see that no matter what your initial guess is, it's quickly heading towards or quickly converging to the root of the equation or the root of the function. And so you're free to go in, change the function however you like, and change your initial guess however you like, and play with this. I encourage you to play with this. Don't bother doing these calculations on your calculator. It will become frustrating, to say the least. All those button presses and you make a mistake. And right here, everything's implemented already, and you can go in and just change whatever you want and execute it. So I wanted to make this available to allow you to focus your attention on understanding Newton's method and how the initial guesses change what's going on. And I don't want you to spend all your time focusing on the arithmetic. That's the secondary thing. The arithmetic, you can leave that to a computer. I want you to focus on the big picture understanding. So that's why this is available, so you can take away the tedious calculations and have the computer do those. So have fun with this, and feel free to explore the rest of the examples that we do throughout this lecture. Okay, in this next example, let's use Newton's method to find the square root of 2 to 8 decimal places. Okay, again, the thing to note is Newton's method applies to finding roots of functions. So the thing to note here is that the square root of 2 is the positive root of the equation x squared minus 2 equals 0. And we're going to call this f of x. So now we've taken this statement and translated it into a question about a root of a function. So our function in this case is x squared minus 2. We want to approximate a root of it. We're going to use Newton's method, so we need to know its derivative. And then we're going to use Newton's iterative formula. So what's Newton's iterative formula? Well, it says you can get the next approximation by taking the previous one and subtracting off f of xn over f prime of xn. And we can now say, okay, well, f of xn is xn squared minus 2. F prime of xn is 2xn. And I can do a little bit of simplification here, putting it over a common denominator. Xn squared plus 2 all over 2xn. So I get a xn squared plus 2 all over 2xn, which is, I can factor out a half, and I get an xn plus 2 over xn. And so there is our Newton's iterative formula for this particular example. So now I need to know an initial guess. What should my initial guess be? Well, the square root of 2. 2 is between 1 and 4, so the square root of 2 would be between the square root of 1 and the square root of 4, so it would be between 1 and 2. So maybe I'll take my initial guess to be 2. You could take it to be 1, or you could even take it to be 1.5, since you know the square root of 2 is going to be between 1 and 2. Now that you know that we have this computational tool that you can just sort of feed in the initial guesses and crank away and see what happens, you should be free to try different initial guesses and just crank away, see what comes out, see the approximations as they come out, and how changing the initial guess changes the degree of accuracy of those approximations. Maybe it takes less time to get to the approximate value to within the number of decimal places you require if you make a better initial guess. In fact, you probably think it should. Good initial guess means you should get to the approximate value of the root much quicker. So we've got our initial guess. Now we just pop it in to get the next guess, or the next approximation. So this becomes 1/2 of 2 plus 2 over 2, or that's going to be 3/2 or 1.5. So in other words, if you were to make your initial guess of 1.5 to begin with, then you would just be picking up right here where we where we're leaving off by taking our initial guess to be 2. So you would have been one step ahead if you made a better initial guess of 1.5. So now we take 1.5, feed it back into our iterative formula, and see what we get. And feel free to try this yourself and see what numbers come out. Use the Sage cell that I just demonstrated for you and see if you get the same results that I do here. So feeding it in, the next bunch of approximations are as follows. Okay, so we worked out the first 6 approximations and we're trying to find the answer to 8 decimal places. So I'm looking at successive approximations to see if I've got 8 decimal places in common. So this is 2, okay, so 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 decimal places there. And this one has the same 8 decimal places in common. The one previous doesn't. So these ones agree to 8 decimal places. And so that means we've just found that the square root of 2 is approximately 1.414256. Okay, so at this stage you may ask yourself, I could use a computer to work out the square root of 2. So did you actually do anything here? Because we did use a computer to work out these successive approximations. But think about what operations we had the computer doing. We had it working with this iterative formula. What's the iterative formula doing? Well, it's taking your input, adding it to 2 over your input, and then multiplying it by half. So all it's doing here is addition, multiplication, and division. It's just doing those 3 arithmetic operations, addition, multiplication, and division. That's all we're asking the computer to do here. And we had it work out an approximation to a square root. So that's the key here is, yes, we did use a computer, but we only had it doing very basic things. Addition, multiplication, and division. Okay, so let's have a look at this next example. We want to use Newton's method to solve this equation, x to the 1/3 equals 0, by taking x naught equals to 1. So here's our function, that's f of x. F of x is equal to x to the 1/3, and we want to use Newton's method to find the root. Well, wait a minute. Why would we use Newton's method to find a root? We know that the only value which has a cubed root of 0 is 0 itself. So we already know that the solution to this is 0. So there's no point in applying Newton's method. Well, okay, the point here is to not apply Newton's method to find the root. It's to apply Newton's method to a case where we know what to expect as an answer. We expect Newton's method to return 0 if it's going to give us an approximation for the root. So let's see what happens when we apply Newton's method. We need to know the derivative. So this is going to be 1/3 x to the negative 2/3. We're going to write down Newton's iterative formula. And what does that become? Well, Newton's iterative formula says the next approximation is the previous one minus the function value at xn over its derivative at xn. So that's xn minus xn to the 1/3 all over 1/3x to the 2/3. And that becomes then xn minus 3xn, because that xn to the 2/3 can come up, combine with the xn to the 1/3 to give us an xn to the 3/3, which just becomes xn. So this becomes negative 2xn, and that's xn plus 1. So there's a nice compact expression for Newton's iterative formula. Let's start with our initial guess. Okay, here we're calling it x0. x0 is 1. What do we get as our next value? Well, plugging that into our iterative formula, we get it's negative 2 times 1, or negative 2. Plugging that into our iterative formula, we get that it's negative 2 times the previous one, so negative 2 times negative 2 is 4. Okay, plugging that in again, becomes negative 8. And we see that every time we take the approximation, plug it back into our iterative formula, we just end up multiplying it by negative 2. So what's happening is our sequence of numbers is not getting closer and closer to 0. Our sequence of numbers is actually getting bigger and bigger and bigger, bouncing back and forth on opposite sides of 0 on the real line and heading off to infinity. So the thing here is that if we continue this, we see that xn does not converge. So what does that mean? It means Newton's method failed in this case. Now, there can be different reasons for why Newton's method fails. The most common one you're going to see in practice is you probably failed because you didn't take a good initial guess. You want that x0 value to be good, so that it's nice and close to the root, so that when you apply the formula you get closer and closer and closer. If you take it too far away, as we've seen in sort of the more dynamic examples that I did with the applet, the sequence of approximations can head away from where you're trying to go to, where you're trying the actual value of the root. So Newton's method failed. In this case, why? Well, was it because we took x naught to be 1? Maybe if we took x naught to be closer to 0, it would have worked. Maybe x naught to be a half. Well, that wouldn't have worked either, because each time we're taking our initial guess and multiplying it by 2. And then there's this sign adjustment, either positive or negative, because they're going to alternate. But you're going to be taking the magnitude of your approximation, and you're going to be doubling it, and then doubling that, and doubling that. So no matter what your initial guess is, if it's not 0, if your initial guess isn't exactly the root to begin with, then you're never going to converge to the root in this example. So this is just an example to be aware of, that Newton's method is really highly dependent on that initial guess. And if your initial guess is bad, Newton's method may not give you a conclusive answer. It may not converge into that root, so you might need to readjust your initial guess. So the picture for what's going on here really looks something like this. We have our function x to the 1/3, which looks like this. We take any initial guess. Here we took 1. There was our initial guess. Our roots there, the origin, that's what we're trying to hone in on. So there's our root at the origin. And from our initial guess, we construct the tangent line. Gets us out here. And if that was 1, then as we saw, this is going to be -2. And then we come down here, take its tangent line, and then go up and take its tangent line. And every time we do this, we keep getting values that are farther and farther away from our actual root. So due to the shape of this graph and the fact that we're using these tangent lines to get our next approximations, things are going away from the root. Okay? Just something to be aware of, that these examples exist. So let's have a look at this last example. We have a function x cubed plus 3x plus 1, and we want to show that f has, this should say has exactly, so we want to be even more precise here. It has exactly one root in the interval -1/2 to 0. And then once we know that there exists a root, in particular exactly one root, then we're going to try to approximate it. So why do we know it has exactly one root in the interval? Well, here's the thing. We've got this function, which is continuous. And let's look at the function value at the endpoint, because I'm hoping that one of them is going to be positive and one of them is going to be negative, so I can then conclude by the intermediate value theorem that there's a root between them. So what's happening at -1/2? That's -1/2 cubed minus 3/2 plus 1. So that's -1/8 minus 3/2 plus 1. Well, I already know -3/2 plus 1, that's a negative number, and then I've got another -1/8, so I know that's negative. What about at 0? At 0, it's 1, so that's positive. So we have that it's continuous on an interval, it's negative at one endpoint, positive at the other endpoint. So by the intermediate value theorem, f has at least one root in the interval -1/2 to 0. We have at least one root. Okay, but we want to show that it has exactly one root. So what we're going to do is we're going to just suppose that there's more than one root. And we're going to try to get a contradiction. So towards a contradiction, in other words, we're going to try to assume that there's more than one root, so assume there's two roots, and try to get something absurd, something that can't actually be true, something impossible. And so then our assumption had to be incorrect. So towards a contradiction, suppose f has at least two roots. And we'll call them x1 and x2 in this interval -1/2 to 0. So suppose there's two roots. what can we say about these two roots? Well, what do we have? We have that f is continuous on the interval x1 to x2, actually including those endpoints. We know that f is differentiable on x1 to x2. And that information alone tells us that we can use the mean value theorem on this interval. In particular, maybe I'm using Rolle's theorem here, but we'll phrase it as the mean value theorem. We know that f of x1 is equal to 0, f of x2 is equal to 0. So by the mean value theorem, or in particular Rolle's theorem, we have that there is a c, a value c in the interval x1 to x2, which just happens to be a subinterval of -1/2 to 0. So there's a c in the interval from -1/2 to 0, such that, so that f prime of c is f of x2 minus f of x1 all over x2 minus x1, but f of x2 and f of x1 were both equal to 0. So there's a place where the derivative is 0. So all this so far was just to say, suppose I have two roots on the interval -1/2 to 0, which we've called x1 and x2. So I know the function has to pass through those 2 points. Then there has to be a place in between them where the derivative is 0. Maybe something like that, who knows. But there is a place, by the mean value theorem, there has to be a place where the derivative is 0. So that's what we called c. Okay, so we have to have a place where the derivative is 0 on this interval, if it has at least 2 roots. But is there a place where the derivative is 0? Let's note that the derivative is 3x squared plus 3. So f prime of c equals 0 means what? Well, it means that 3c squared plus 3 is 0. Or in other words, c squared is -1. So this place where the derivative is 0 has to be at a number c whose square is -1. But there is no such c. No such c exists. There is no real number whose square is -1. So this is impossible. It's impossible that there's a place where the derivative is 0. And that stemmed from our assumption. What was our assumption? We supposed that f had at least 2 roots. And from that, we got something that was impossible. So our assumption had to be wrong. F cannot have at least 2 roots. But we already know that it has at least 1 root. So it has at least 1 root. It can't have 2 or more roots, so it has to have exactly 1 root. So those 2 bits of information together tell us that therefore f has exactly 1 root on the interval -1/2 to 0. We are guaranteed the existence of a root by the intermediate value theorem, and we managed to show there couldn't be 2 or more roots by the mean value theorem. So we have exactly 1 root. Now the next part of the question says, okay, you now know there is a root, try to approximate it. So this means we're going to need to use Newton's method. So x cubed plus 3x plus 1 is our function. Our derivative is 3x squared plus 3. Our Newton's iterative formula is going to be xn plus 1 is equal to xn minus f of xn all over f of f prime of xn. And so in this case, it's xn minus xn cubed plus 3xn plus 1 all over 3xn squared plus 3. So that's our Newton's iterative formula. We just need a good initial guess now, and then we just need to start iterating. So what should our initial guess be? Well, we're on the interval -1/2 to 0, so maybe I'll just take one of the endpoints. Maybe I'll take 0 to be our initial guess. And so x2, well, I can pop that in and I get negative 1/3 coming out of the iterative formula. Putting 0 in for xn, I get negative 1/3 out. And then I take that and I plug it in. And at this point, I'm just going to use the computer to do the rest of these iterations. And so I use the computer to start cranking out all these iterations, and I get these values. And we were asked to stop when our iterations agreed to 2 decimal places, and we see here that this iteration has 2 decimal places, 3 and 2, and this next one agrees to it. So these agree to 2 decimal places. And so the root is approximately negative 0.32. Okay, that's it for this section. Thanks very much for watching, and we'll see you again next time.